I try to remove.
Yeah, okay.
Wait, I need to press OK.
Okay, yeah. Welcome to the Monday seminar, everyone. Nice to see you. I am been running this for a while now, and it's one of my favorite things to do during the week. So it's really wonderful to see so many familiar faces. And we're very lucky to have Ann Obermann with us today to talk about some work she's been doing for a while on the seismic response of fracture systems to hydraulic stimulation. So without any further ado, I will invite Ann to go ahead and thank her for being with us. Go ahead, Ann.
Yeah, thanks, Chris. Thank you very much for giving me the opportunity to talk to all of you and tell you a little bit more about what we have been doing in this first series of hydraulic stimulations over the past more or less 2.5 years in Switzerland. 1 second. So I will briefly sketch the initial motivation that we had to undergo the tremendous effort to actually construct this Bedretto laboratory. And since the installation is quite unique, I will have a handful of slides on the monitoring system and the challenges that we encountered at these mesoscale experiments. And then I'll talk about the seismic response of the first experiments. And yeah, in the unlikely event that I talk way too fast and still have time, I'll show you some ongoing analysis on like focal mechanisms or template matching. So let me get started. Like the Swiss energy strategy for 2050 foresees that this big part of nuclear is fading away and reduced, since the overall energy load is expected to remain pretty similar. This energy needs to be replaced. And this is where a huge load of renewable energy sources are coming in. So the hope is that by 2030, 40, that there would be about a 7% or so of the load produced by deep geothermal. This was the initial motivation, was one of the motivations behind that we want deep geothermal to play an important role in Switzerland. And to reach that, well, we have had the challenge in Switzerland that induced seismicity has been associated with deep geothermal energy production. There were the two experiments in Basel and St. Gallen that both produced, unfortunately, earthquakes of a magnitude 3.4, 3.5, and that hindered the further development. Induced seismicity is not unique to geothermal, has also been seen in Switzerland with heavy rainfalls, tunneling, or unloading and loading of large dams, but certainly received more media attention when it came to geothermal energy production. Switzerland is not alone with this problem. There are worldwide many projects or engineering projects that have produced induced seismicity, often much larger than the 3.5 earthquakes in Switzerland. So at the moment, let's say, or the main limitation that we saw is how do we go from the laboratory where we can gain knowledge in really well-controlled experiments on the small scale, like from, let's say, 10 centimeters to a meter. How do we go to deep experiments that are at a scale of 2 to 5 kilometer depths, where knowledge of the local conditions is typically quite limited? It's in a normal setting, you only have your information coming from the surface. So a solution could come from having larger in situ experiments that allow us to still monitor the rock volume in a very well controlled or fully controlled setting, but that at the same time where at the same time the experiment is exposed to realistic stress conditions. So this is where the idea then came from, to go to the hectometer scale, where we would be really in between the laboratory and the real field scale. Sorry, 1 second. I have your names all in between on my screen. Yeah. Well, So to conduct these fully controlled and repeatable experiments, yeah, we need to go to larger scale and use higher water pressures. 1 second, I need to remove this. Okay, I don't see my screens. Okay, and so one of the goals for these in situ experiments at hectoscale would be to validate protocols and procedures prior to the deployment in deep enhanced geothermal systems, to provide test beds for experiments, models, monitoring technologies, and of course to develop and test other innovative methods to really create and use geothermal reservoirs, and also to strengthen the public confidence. So we thought we should set up such a deep underground test bed in Europe to conduct experiments in several areas. One of them is water injection, water circulation, reservoir formation, and where many of the people attending this seminar here are more involved with would be fault stimulation and earthquake physics. While we have lab shear experiments and at the 0.01 to 1 meter scale, and we have seen decameter injection experiments at 10, like Grimsel or Sanford Asper, they produced very successfully results. And what we want to do here is then scale this up, go to 100 meter, about 1,000 meter deep, where we expect that we are reaching really relevant depths and volumes that are representative to small-scale field reservoirs, and to stimulate in these settings. And well, Domenico Giardini has been very successful to convince the Swiss authorities that this is exactly what we need. And we found an abandoned a tunnel facility that we could use. That is this Bedretto tunnel in southern Switzerland and Tessin, close to Airolo. And since 2018, we have now been developing a new underground research facility in this tunnel in the Swiss Alps. Here we have an overburden of about 1 up to 1.5 kilometers. And we have access to a rock mass that is really comparable to shallow crystalline reservoirs in terms of stress condition and also structure. And this lab is located in total 5.2 kilometer long side tunnel of the Forca railway tunnel. It was completed in 1982 and was originally used to facilitate ventilation and drainage of this Forca-based tunnel. And yeah, ETH was then given access to build a research infrastructure in the tunnel. The experiments that I present you, they all took place in a niche that is at about 2 kilometers inside the tunnel, where we drilled 6 hectometer long boreholes or monitoring boreholes and 2 additional injection and production boreholes. And the context of these experiments is geothermal. The niche here, where we're looking at, it is situated in Rotondo granite, which is a roughly here outlined 300 million year old pluton. And there is deformation going on in these rocks, or these rocks underwent deformations throughout the alpine orogenesis, and this can be seen in form of weak foliation and narrow northeast-southwest trending ductile shear zones that we see in this area. And the structures here shown in the core, they give you an idea of how this material looks like. So we have, for example, here on top, a core from the Rotondo granite that was cross-cut by a quartz vein. And we have here on the bottom some brachia with clasts that are surrounded by some dark fine-grained matrix. And here a mylonitic ductile shear zone that is quite nicely showing up. These are some pictures from the Bedretto tunnel as it looked like in 2018 when we started entering the tunnel. It was unpaved, At some parts, you had to walk knee deep in water. And this place was turned into really a neat research facility with electricity, ventilation, and all the conditions that you need to conduct large experiments. High-speed internet cable connecting it directly to Zurich, etc. So with that, let me go to the multi-parameter monitoring system that we installed. So we encountered various challenges for experiments here at the hectometer scale. While there are sensors available that you can use for deca scale, for the decameter scale, and also at field scale, here we encounter the challenge that in particular for seismicity, we want to cover a very large magnitude range. We want to cover -5, -6, but also have potentially events going up to -0.5, 0.5, and eventual local seismicity. So this is a very large frequency range, and there are no adapted or no sensors that can, there is no one sensor that can cover all of these frequency ranges together. So we need to take this into account and install different types of seismic sensors for the experiments. The scales that we want to cover is, on the one side, the local seismicity, where we make use of the backbone network that was in the area and densified it. And then we have, for the research purposes, we have we are interested in microseismicity down to picoseismicity. And here the frequencies go very high, and we work with, in particular, with geophones, accelerometers, and acoustic emission sensors. The results that I show you here, they are from these IE sensors and the accelerometers. Yes. So besides, there were other challenges, or there are other challenges related to the sensor placement, installation, and site conditions of the sensors. So in these a few 100-meter long boreholes, there is substantial deviation during drilling, which requires constant adaptations of the network design. Also, the exact measurement of the sensor position is quite difficult, and less certain the deeper you go into the borehole. Regarding the installation, since drilling long boreholes is expensive, the total number of boreholes is limited, and so in each of them we need to place various types of different sensors. This needs to be designed carefully so that none of these sensors break while instrumenting them. There is also risk of breakout zones, debris, or we were quite worried in the beginning of our sensors getting blocked or any of the cables rupturing during installation. One of maybe the most challenging parts were the high requirements for the sensors themselves. Since we encounter very high pore pressures at depths, the sensors must be absolutely water and pressure resistant, and at the same time remain small enough to fit the boreholes. And also the electric cables, they all needed inner sealing to prevent water from entering. We produce, especially also with dust cables, quite a lot of data. So during a stimulation day, this can reach more than 1 terabyte per day. That needs to be in real time streamed outside the tunnel. So over a period of about 2 years, we spent quite a lot of energy and time on prototype development of almost all of these sensors. And this was not done in-house, but was in-house, accompanied, and done together with specialized companies. So in total, we drilled 8 boreholes from 150 to 400 meters. These pictures here show you some exemplary features that we encountered in the boreholes. So there are step overs, borehole breakouts that you can see in some parts, clearly visible shear zones, the bottom, and borehole blockage by rock fragments. And this footage has caused us a lot of headaches before, but to anticipate it, actually they did not cause trouble during installations. So there have been substantial efforts to characterize the in situ stress conditions and internal structures of the rock volumes, also based on the information that we have once the boreholes were drilled. And so Kai and Xiaodong in Brücke and Mar, they worked, they determined the fast stress field orientations, briefly sketched here, with the maximum principal stress component as one that has a magnitude close to the overburden stress and a direction close to vertical. So in general, the stress state is not critical. However, they observe rotations of the stress field in a little counterclockwise direction in a group of shallow boreholes. So this is very likely just a local perturbation, but it shows that the stress field is very heterogeneous and easily influenced by fractures and fault zones. So the installation itself, it always starts with a guide shoe that contains a geophone inside. The purpose here is to record microseismicity, and one of the main challenges was to really seamlessly cement the borehole into the guide shoe as well. Then we have here a picture of the instrumentation. Here you see the guide shoe, and then we have every 3 meters, we have centralizers to just make sure that our instruments are not touching the borehole wall and not being destroyed during the installation. This whole equipment is getting quite heavy. So on a 300-meter borehole, we easily have 600 kilos or more hanging there. These are some of the main or most important sensors here, the acoustic emission sensors. So they are highly sensitive for measuring really the tiniest seismic events that we have. The main challenge is to have them waterproof and pressure resistant. And this does not so much regard the IE sensor, but more the preamplifiers themselves. And yeah, we place them on a chain with 12 channels together with also accelerometers. So this is like a view of one of these chains that we then install in the borehole. In each borehole, we also have ultrasonic transmitters. The purpose is that they can help to observe changes in elastic rock properties. And here as well, they need to be resistant to pressure, and the signal strength needs to be sufficient to actually reach our receivers. The most boreholes are also instrumented with fiber Bragg sensors and fiber cables. So we have DTS or temperature sensing, strain, and acoustic and DAS cables in the boreholes. In a couple of boreholes, we also have cementable pore pressure sensors. Here, the challenge was that we want to make a pore pressure measurement actually in an open borehole, collocated with strain monitoring in a cemented borehole. So we came up with some membrane, or like with some tube membrane structure that I think is producing quite okay data. So this is how this looks like. And we would also clamp that on top of the rod for instrumentation. This is how it looked like in the tunnel. So it took quite a while to instrument the boreholes, about twice 2 weeks, I think it was. Yeah. Of a group of people working. And yeah, so after installation, the boreholes need to be sealed in their full length with a fit-to-purpose cementation to minimize the impact of impact on fluid passes or strength or stress conditions. I will not go more into detail here, but just to make you aware that even this seemingly simple step is actually a science in its own and caused quite a lot of headache as well. So our final monitoring system then looks like this. We have 6 instrumented boreholes that took twice 2 weeks to instrument for 8+ people, and that were followed by 1 week of cementation each. For the seismic monitoring, we have three component no, this is wrong. We have 5 3-component geophones, actually one at the bottom of each of the boreholes. One was leaking, not working so well. We have 5 accelerometers, 34 acoustic emission sensors, and 12 functional ultrasonic transmitters. The surface network in the beginning, excuse me, I'm on earthquake duty. I just need to silence the phone. Sorry. So we have on the surface 3 strong motion stations, a broadband stations, and additional stations. I think by now this is much denser since since there was a lot of effort to densify also the microseismic observation capacities. And for geomechanical monitoring, we have 58 fiber brake sensors, 4 cementable tube pore pressure sensors, DTS, DSS, and DAS. And in ST1, so then we have these 2 long boreholes, ST1 with a multi-packer of 14 injection intervals, and ST2, which in the future might be a production borehole. So it is actually quite a unique situation to have collocated sensors of so many different types that hopefully will allow us to gain quite some novel observations and help us to understand really the full rock response of what is going on during the stimulations. So let's have a look at the seismic responses of the first experiments. The goals of these first experiments was in the context of the so-called Project Walter. Walter stands for Validation of Technologies for Reservoir Engineering. So we wanted to make this large-scale in situ experiment to address questions associated with validations of stimulation procedures and sustainable utilization of heat exchangers in deep underground. And at the same time monitor hydroseismic mechanical parameters at a high spatial resolution. So we are working on answers to questions. I say working because we don't have all the answers yet, to say which stimulation concepts are actually appropriate for enhancing permeability by orders of magnitudes while minimizing induced seismicity, or what are relationships between the hydromechanical response, stimulation concept, permeability creation, effective porosity, and induced seismicity. How can we minimize seismicity, induced seismicity, and what are actually the heat exchanger properties of the reservoir? So this Bedretto test bed was conceptually designed to consist of volumes with different levels of receiver coverage. So here in what I will present you, we focus on a central area that we refer to as high resolution monitoring zone. And this covers the top 8 intervals. So starting at interval 7 at the edge of this high resolution monitoring zone, and then going up to interval 14. Deeper intervals in ST1 here, they have been stimulated prior to our experiments in the so-called de-stress project, but I will not report on results from that project. And in this volume here, we know from acoustic and optical televiewer logs that the main strike directions are well in line with geological observations, and that the rock volume can be divided in roughly 4 units. So we have a first unit on top with fractures mainly in north-south direction. Then we have a transition to north-south, southeast, southwest oriented fractures, northeast, southwest, and the 4th unit would be again a tilt to northeast, southwest, northwest, southeast. In between this unit 2 and 3, there is the largest fault zone in the area that we initially referred to as bad boy fault zone. And that is quite noticeable on the logs, and that we also see in our results. So the stimulation concept that we had for for these first set of experiments was that we applied a two-phase approach for the development of this model reservoir. So in a first phase, that is shown in a very slow video on the left, the first phase we refer to as characterization phase, where we visited each of these 8 intervals with a standardized injection protocol. And this allows us then to compare the influence of the targeted geological structures to the seismohydromechanical response. An example here you see here on the left. And then in the second phase that we refer to as reservoir engineering phase, we revisit intervals that have shown interesting behavior in phase 1. This could be in terms of seismicity, transmissivity, or pressure evolution, or anything that captured our attention. And if we revisit them once, we talk about 2A, twice, 2B, and so on. At this stage, we have different protocols that we adapt to what we expect or want to see or control in each of these intervals. In the future, a third phase should be dedicated to actually doing a circulation experiment of fluid or heat. So in this characterization phase, the injection protocol typically consisted of 2 cycles, and in which either the injection pressure, as shown here, or the flow rate was increased in a stepwise manner after a quasi-steady state condition was reached. So in this first cycle, we then determine the approximate range of the reactivation pressure, and then in cycle 2, we refine the knowledge of that using smaller increments of pressure or flow rate. Yes, so here this is, and on the right, this reservoir engineering is shown as an example for interval 11, which was actually very unspectacular in phase 1, but nevertheless, we revisited this interval 2 more times, so I think by now several more times, here with cyclic stimulations to alternate between constant flow rate, injection, and shut-in phases. And we wanted to see to which extent the seismic patterns are actually repeatable, like whether seismicity kicks in at the same flow rates or pressure. And during the first phase, this characterization phase, we did a total of 8 stimulations and injected fluid volumes between 0.3 and 14.1 cubic meters. The largest magnitudes per interval ranged from -2.3 to -4. And we had event numbers very small, like less than 100, going to up to more than 5,000, for instance, in interval 13, which contains this main fracture zone that we saw before. In the reservoir engineering phase, I report on a total of 6 stimulations where we injected fluid volumes between 2 and 270 cubic meters. The largest magnitude that we observed was a -1.6. Yes. So here I show you an exemplary seismic record from a -2.57. That shows very clear recordings of P and S waves and velocities of about 5.4 kilometer per second and 3.1 kilometer per second, respectively. Depending on the station location, the medium shows strongly scattering P and S wave coda trains. And local attenuation effects are likely also responsible for the sometimes delayed S phases. So on the right, you see some exemplary power spectral density plots for various events ranging from -4.8 to -2.2. And at the top, you see them at close distances of about 16 meters and at the bottom at larger distances of 80 meters. What you can see is that all signals are clearly above the noise, which is a gray line here and here. But you also see that we observe a loss of high frequencies quite prominent here for all of these magnitudes already at distances of 80 meters. So which means that you need to be really close if you want to study higher frequency events. We also encountered transient electronic noise, which is shown here, which is a quite common problem in acoustic emission recordings. This noise arises due to electromagnetic crosstalk, and especially when heavy electric machines like pumps are on site. And we could quite successfully reduce the electronic noise by incorporating frequency filters or insulating transformers. We could reduce it to levels that were acceptable without doing additional filter operations while processing the data. So we are quite happy with that situation. And to gain an understanding of the spatial variability of our network, we also looked at the sensor magnitude with event sensor distance that we can record. And we see that here I show single sensor magnitudes, and they follow very clearly a linear relationship with distance, starting here for events larger than 15 meters. This means that, for example, at distances of 15 meters, we can detect events of magnitude -4.95, and at distances of 50 meters, we can still detect magnitudes, or lowest magnitudes that we can detect at those distances are about -4.3. The very near field here seems to behave a little bit different with a slightly steeper slope, but yeah, I think this could as well be an artifact. Not shown here, but for large events, the IE sensors clip amplitudes for magnitudes of -3 at distances of less than 20 meters, or -2.4 for distances at 40 meters. But since we have the borehole bottom geophones in place, and also accelerometers in a network that extends actually over more than 150 meters, even for our largest events of -1.6, we still have more than 10 unclipped recordings. But this could be a challenge if we want to go to produce even larger magnitude events. So to construct the seismic catalog, we started from the continuous data streams that are sampled at frequencies of 200 kilohertz in ASDF format. We choose this format because it allows for flexible and fast access to the data, and is also integrated in an open source Python library that we used for event detection. And the typical recording started a few hours prior to one of our experiments and was then kept running for a handful of days afterwards. Data was directly streamed to a server in Zurich, where the seismic data alone is producing about 470 gigabytes a day. For the processing then, we differentiate 3 steps. So we first do a quick pseudo real-time processing to monitor the generated seismicity during the stimulation, and to be able to raise alerts if magnitudes of an event exceed a certain threshold. We call it pseudo real-time, since the ASDF files need to be written first and before they can be accessed for processing. And this adds a delay in the order of the file length, which in our case was about 10 seconds. So we then, at this step, apply an STA-LTA picker on the 5 closest stations to the stimulation interval. Step 2 is then a more precise, still fully automated reprocessing of the events that starts directly once the events come in, to refine their locations and magnitudes, and to have a better image of the spatial distribution of seismicity. Here we use multi-frequency bands, a multi-frequency band kurtosis picker, also called FBKT. And we relocate and re-estimate the magnitudes of each event with at least 5 of these picks. Such information is then available with a delay of 30 seconds to a minute to the origin time of the respective events. Step 3 is to create the actual high-quality catalog that we then use for research. And here in this post-processing, we improve the picks with FBKT KT and also IKE picker, and we include detections of low magnitude events. So we actually rerun these picks on all stations, and with a decreased detection threshold and a refinement on the picks. And as the last step, we do an absolute location and then a relative hyper-DD relocation of the events. In the beginning, we manually checked the highest magnitudes to be sure that the values make sense. This is an example of the real time of one of the intervals and how this looks like the catalog for the real-time processing. So in light gray, you have the STA, LTA real-time locations, and then in black, the FBKT locations, where you already see a refinement and better clustering of the structures. Then in post-processing, when we apply this to all stations, you see that the number of events dramatically increased. And here in black, with the IKE refinement, you see that also the clustering is getting better. The additional step then for relocation is actually relatively small. I think the largest step is really going here from the quick real-time assessment of what is going on to the first post-processing. Yes. So in general, in experiments that produce picoseismicity, one key challenge is to compute the magnitudes from these highly sensitive but unfortunately uncalibrated acoustic emission sensor recordings. And the lack of calibration means that we do not have an instrumental response available to correct our recorded signals and really compute an absolute magnitude, moment magnitude. And to tackle this problem, what we did is that we installed these collocated sensor pairs of acoustic emission and accelerometer. And then we used these sensor pairs to extract a calibration function that we can apply to all other acoustic emission sensors and to adjust these relative amplitude magnitudes to a realistic magnitude level. And such a relationship that we obtain is shown here. And we see that it is quite robust for over 3 orders of magnitude. And we will then apply this correction term here on top to all of these amplitudes, voltage amplitudes that we measure. And last year, there was actually a dedicated calibration experiment in a salt mine to further improve or to obtain an instrument response from different types of acoustic emission sensors. I think Paul is working on a manuscript on that. So here I show you a first view of the seismicity that we recorded. And I show this before I take you actually through the individual intervals. And oops, so I want to put your focus on some general observations that you can also try to see in the next slides in the individual observations. So one general observation would be that the volume impacted by the stimulations of these different intervals differs quite significantly with lateral extent. So we have stimulations that have, here each interval has a different color. So you have stimulations that stay very close to the injection point with a lateral extent of only a few meters, whereas you have other stimulations that are here on the right, plotted in a different graph, like this interval 8 here, that expands over more than 130 meters. Most intervals, as you can see, they actually activated multiple fractures, and only during stimulation of interval 13, as we will see the next slides, one single very long fracture was activated. Seismic clouds typically propagate upwards towards more permeable, shallow depths, and this happens on parallel dipping planes. These planes are consistent with the stress field and seem to a large extent associated with pre-existing open fractures.
And it's Chris.
Yes?
The interval, the injection interval is always the same. It's about 10, 20 meters long. How long is it?
It goes from, so I will show in the next slide. So it goes from 7 to 50 meters. So it's not always the same length. No.
I see. Thank you.
Yes. So let me now take you through the individual stimulations. So here I start with two relatively boring cases, interval 7, that is 35 meters long, and interval 14 of 55 meter. Both of these intervals are at the edge of our dense seismic monitoring network. So interval 7 contains many filled fractures, some undifferentiated fractures, and two fracture zones where we could even detect outflow. Because of these structures, this interval was the second most transmissive in this entire Walter volume. And during the stimulation of phase 1, we detected around 400 events. But as you can see, seismicity was quite scattered, with a lateral extent of about 90 meters and no clear alignments along planes. This might be related to a reduced sensor coverage. Interval 14 is mainly intact rock with many filled fractures, and on the logs we could only see 2 non-filled fractures. Yeah, so it's not surprising that the transmissivity is very low in this interval, with like 5 to the -9. And during a meter, square meters per second. And during the stimulation, we detected around 460 events, but only half of them fulfill the criterion of high quality, which would be that you have at least 8 peaks and 40 navies. And you see also here the seismicity is quite diffuse with no clear alignments. So it becomes more interesting when we go to interval 8. Interval 8 is 30 meters long. So 8 is from the bottom, we are going upwards. And it has 2 prominent non-filled fracture zones that mark the boundary between this unit 3 and unit 4, where we have a slight change in the strike direction. But despite these very large, or these larger fracture zones, the transmissivity is rather low, or much lower than in the neighboring intervals. During this characterization phase 1, we detected around 2,000 events that extended over the order of 50-55 meters and were mainly located in the upper part of interval 8. Time if you look at the time behavior, there is a moving towards the ST2 borehole. Interval 8 actually also showed a strong mechanical connection to deeper parts of neighboring boreholes. And there was a 7-fold increase in transmissivity after the stimulation. So we hence decided that we want to visit the interval again. And we did this with a much larger injection. So this time we observed more than 12,000 seismic events, and the spatial extent of the seismic cloud exceeded 130 meters. So you can see easily that several fractures were activated during the stimulation, covering really different depth levels. The stimulation lasted in total 2 days. So you have different colors here, indicating the time behavior. And this stimulation resulted in an additional increase of transmissivity of a factor of 4. Yeah, so this is one of our, or this was the largest stimulation that we did during this cycle. Then we have interval 11, which is 18-meter long, and in phase 1, it has multiple non-filled fractures and also 2 fracture zones, but there was not a lot of seismicity occurring during the phase 1 stimulation. Nevertheless, we decided to visit this interval again with larger injections to see if we could repeat seismic patterns here. So during the first re-injection, we produced more than 4,000 events along 2 separate planes here in the top part of the interval. And with time, the seismicity expanded further outwards along the planes, and additional fractures were activated, crossing into interval 12 on top, and also in the lower part of the interval. So this only happened here. If you look at the colors, most of this came really at the second day of this large stimulation. And this trend was continued with a third stimulation that I show in the next slide, reaching a lateral extent of about 40 meters. So then here we have 2 intervals, interval 9 and 10, that are both relatively short with 14 and 17 meters. And they both contain many non-filled fractures with small aperture. So interval 9 contains also a shear zone and has an intermediate transmissivity, while interval 10 has relatively low transmissivity. And during this phase 1 stimulation, we detected around 800 and 570 events. If you look at these images, you see that the event location in both intervals is very similar, indicating that the same fractures were stimulated. And the lateral extent of the seismicity cloud reached 30 meters with no clear spatial or temporal evolution. If you look in detail, there are 2 separated planes that were activated in the upper part of interval 9. And actually there is no seismicity directly around the injection interval 9, but all of it happens on top. Yes, so then we decided, since there is clearly a hydraulic connection between these 2 intervals, we decided that we will jointly stimulate the intervals in phase 2. And to do this, so when we started doing this, the events happened again in the structures that had already been stimulated during phase 1. But then seismicity was observed to really move outwards, activating much larger fractures here of about 50-meter lateral extent, and most of them parallel to the fracture planes that we stimulated in an interval below. And again, no seismicity was observed directly around interval 9, despite the reactivation of seismicity here in a stimulation in interval 8. And this is here to show that interval 12, so here all of these images here have it's the same view and the same volume. You see that also this interval 11 stimulation, the fractures that are activated here, they are part of this fracture system that is much more extended than in interval 9, 10. Interval 13 is also quite interesting. It is 18 meters long and contains the largest fault zone of the experimental volume, this bad boy structure. Above and below the central fracture zone, there are several non-filled fractures, some of them with large aperture. And transmissivity is by far the highest of all intervals. And during stimulation, then we detected more than 5,000 events, and the majority of them showed a very clear alignment with the main fracture zone in the volume, with a lateral extent of about 40 meters. At the beginning here, seismicity occurred in the in the direct vicinity of the injection interval, but then very quickly moved outwards along the fracture planes. Interval 12 is the shortest interval that we have, and during the phase 1 stimulation, you could see very clear and prominent fracture zones. Fractures, but they stay in the direct vicinity of the injection interval, extending or being constrained by 10 to 20 meter lateral extent. We revisited this interval 2 times. Also here we see very nicely the fracture planes that are activated. And then we see in particular here in phase 2, we see that at some point, apart from these 2 already known fracture zones, we have new fractures or different fractures that are highlighted. And again, one of this structure here actually coincides with a fracture that we also observe in the interval 11 stimulation. So I don't expect you to remember all of these things in detail. So now I will show you some figures that summarize our observations. So here, when we look at the relation between the maximum observed magnitude and the injected volume, we intended to fill this gap here in the Hector scale. And these red dots show where we are standing with the experiments that we conducted. And I think we succeeded in filling or in contributing to this gap. And additionally, what we see is there is in general an almost linear increase of magnitude with injected volume, but we also see that we are about 2 orders of magnitude scale below this postulated slope from McGar for the maximum possible magnitude. So yeah, we must have done something right in controlling induced seismicity. If we zoom into the stimulations that we did, here color-coded by interval, and the symbols are for the different phases. We see that only the first 2 stimulations in the interval 12, highlighted here, that neighbor the main fault zone, they show a substantially higher magnitude for low injection volumes. All of the others are more or less in the same range. And then we also see that there are variations in response for different intervals. For instance, here, interval 9 and 14 in phase 1, they have seen very similar injection volumes, but they show an Mmax difference of 1 order of magnitude. And for the reservoir engineering stimulations in 2A and 2B, the intervals typically responded. So here, these are the intervals that we stimulated again, and they typically responded as expected from the characterization stimulations. So here I show you in the top row the normalized cumulative fraction of detected events as a function of cumulative injection volume. And the maximum magnitude is always marked by a star and written beside. And on the bottom, we see the cumulative seismic moment, which is a proxy for active fracture area, versus the hydraulic energy, which is pressure times volume, for the different phases. So this is stimulation 1, first re-stimulation, second re-stimulation. And so we see that seismicity kicks in rapidly once a certain, which seems interval-dependent, injection volume was reached. And this threshold remains similar for repeated injections, if you go from here to here. And we see that for most intervals, also the cumulative seismic moment reaches its maximum with the largest magnitude and does not increase further with increased injection volume. And this effect could be actually related to the limited pump capacity. Because due to the due to the high injectivity and or transmissivity in intervals 7 and 13, which is here, these colors, the pressure and flow rate here actually increase linearly. We look at some statistical properties. I show you here the frequency magnitude distribution for phase 1 and the first re-stimulation, so 2A. And we obtained, or we calculated, these Gutenberg-Richter B-values as a Bayesian hierarchical model, and accounting for injection flow rate and activation feedback parameters. So we observe a quite large scatter in B values, you can see here, and also A values. That seems to reduce, however, for larger injection volumes. So once you add above around 7 cubic meters, the scatter here seems to be reduced, and the same goes for the seismogenic index. The larger scatter we see might correspond actually to significant variations of hydrological and mechanical properties that were already observed during the rock volume characterization. More interesting is here the reduction, and this could be that was the smaller injected volumes. We actually sample a smaller rock volume, and so local fracture properties or stress conditions govern seismicity. While when we go to larger injected volumes, we have larger rock volumes that are sampled, and we smear the local properties. I think that these fluctuations of A and B values with volume could have quite far-reaching implications for the use of small volume injections actually to calibrate seismic hazard forecasts. But we need more observations to conclude whether, for instance, a minimum injected volume is necessary to converge to stable A and B values. And we also need to keep in mind that these small injections here these small injection volumes produce fewer seismic events and hence less stable estimates for the A and B values, which you can see here in these larger error bars for the events. And also for these stimulations, we have too few post-shut-in events to compute A and B values for shorter dedicated time intervals, which could also help to improve hazard estimations. Yes. So here I show you a visual, or I summarize some of the stimulation's key parameters for each stimulation interval. The stimulation interval is given here by the depths of the injection point. And it is color-coded by stimulation phase. From left to right, I plot injection volume, number of high-quality events, maximum magnitude, A and B values, the seismic activation pressure, which I defined as the pressure when the first 5% of seismicity occurred, the reactivation pressure, and lateral extent of seismicity. The gray zones here, they mark the shear zones in interval 13 and the main 2 unfilled fractures in interval 8. And if we only look at the key observables from the characterization stimulation, which are yellow, we observe a pattern like a little like a hyperbola, seemingly sandwiched between these main shear zones in interval 13 and these unfilled fractures in interval 8. And we speculate that the diversity that we see in seismic response correlates first order with the distance to these dominant shear zones and the volume. This could imply that the complexity that we observe on the smaller scale might average out and give way to less complex or more predictable large-scale processes on the field scale. Yeah, that could be determined by the bulk properties of the stimulated rock volume. So to wrap it up, I plot you here the high quality catalog events for all stimulations in a selected angle where I think you see very nice that they fall on parallel planes. To have a clearer image here of the activated structures, I also removed scattering events with more restrictive conditions, so I only plot events with a minimum of 8 peaks and more than 40 neighboring events. So let me summarize again the most prominent observations. So we see that most seismicity follows fracture planes with a predominant northeast-southwest direction, dipping around 70 to 80 degrees and coinciding with the direction of known pre-existing fault structures. We have a spatial extent of the seismic cloud that showed different behaviors for different intervals, ranging from 7 to 130 meters, with an exception of the stimulations in intervals 7 and 8. The largest events occur in the vicinity of the injection points. Here you see 7 and 8 have the largest events occurring quite outside. And seismic events highlight decameter-long single fractures with linear dimensions, in some cases exceeding 130 meters. And in general, I think this yields quite a clear impression of a hectometer-scale fractured reservoir. Many of these experiments, not all of them, but many of them showed concentric growth of seismicity, while for other intervals, seismicity occurred in the same location, suggesting that the same fracture zones were activated. So, yes, I think with these hectometer-scale hydraulic stimulation experiments in Bedretto, we managed to fill the gap between decameter experiments and the kilometer scale of engineering projects. We have a quite unique experimental setup with a multi-parameter high-quality data acquisition system. So we have now our triggered seismic catalogs and continuous waveform data at 200 kilohertz sampling rate, more than 41,000 seismic events with high-quality seismic events, and magnitudes ranging from -5 to -1.6. We observed these complex 100-meter plus fracture networks, and we managed to more or less control the stimulations with magnitudes 2 orders below Mega limit. And yes, I think we have above all a lot of work ahead. And with that, I want to stop, and I hope it was somewhat interesting. Thank you very much.
Incredibly interesting. Thank you very much, Anne. I'll ask people to unmute if they'd like to and join me in thanking Anne for a really interesting talk. Wow, a lot of work. A lot of data.
Yes.
Yeah, fabulous. Well, okay. One of the nice things about this format is that it allows us to have an extended question and answer and discussion period. And the easiest way to make that happen is to use the reaction button at the bottom of your screen. Raise your hand like this. I assume people know. And yeah, Pablo Ampuero has already done it. Please, Pablo, go ahead.
Hello, everyone. Thank you, Anne, for this wonderful observations that you showed today. So you highlighted this, the seismicity seems to highlight this almost parallel fractures. And I wonder if you also see some fractures that are not aligned with those, like crossing them, especially in the cases where, I think you show at least one case where 2 different parallel faults were highlighted by the seismicity. And so I wonder if there's any evidence of flow in between them across other faults that are not aligned.
Yes, so there definitely is. As you said, you can already see it in some of the intervals. We now started to look in more detail at the individual intervals. And there are certainly fracture planes that appear that are almost vertical or at least inclined and not following this main dipping planes. Yes.
Paul Johnson, go ahead.
Thanks, Anne. Super interesting, incredibly complex experiment. Could you go back to your Art Magar plot, showing the Magar line in contrast to your data?
1 second, let me go back. Sorry, a little slow. Can you see it?
Yes. The I guess my question, Ann, is you're well below the limit that Art McGar predicts at these ejection volumes and associated magnitudes. Do you think it's because you have unique physical properties of the material here, or do you think it has to do entirely or partially with your injection protocol? Or do you know? Do you see what my question is?
I see your question, and I need to say I don't know yet. Like, we are planning at the moment an experiment, what we call M0, where we actually try to adapt the injection protocol to go higher, to reach these limits. So I think in a couple of weeks I can maybe tell you more about that. But I'm not sure at the moment of whether this is really the way we stimulate it, because we tried also to precondition or to do other things to increase the magnitudes. But yes, I don't know yet.
Okay, thanks. I mean, it's a really important question, right? If you
Yes,
have
yes.
devised a way to control magnitude, I mean, this would be spectacular. So
Yes,
incredibly.
we need to double check before we are sure about that.
Yeah. And one other question, sort of point of technical question. You mentioned you had electromagnetic crosstalk and you were able to filter that out. Did you have mechanical vibration as well from the pumps that caused any problem?
Not in this experiment, and I think that is because our sensors are in these cemented boreholes and quite below. And no, mechanical vibrations were not a problem here. I think
Great.
they were in Grimsel, so at the decameter scale, but no, we did not have an issue. We did not have to do anything specific to really put them on a foam or anything. This worked. This was fine.
Okay. Thanks so much, Ann. Fascinating experiment. Really
Thanks,
appreciate
Paul.
your time.
Yeah, I agree, Ann. Really nice talk. And Greg, if you're okay, if you can just hang out a second, because there was a question in the chat from Bowen Yu. And maybe we could just get Bowen to join us and voice that question. Bowen, would you like to do that?
Oh, yes, great, thanks. I don't find the button for raising hand in my
Ah, I
so
see.
okay, thanks for your talk. My question is that I'm wondering if you have observed some casing deformation during the hydraulic stimulation. Thanks.
Well, I mean, we don't have access back to the borehole, so I couldn't tell you if the casing really deformed. Actually, we don't have casing. I mean, we cemented these boreholes, but so the strain data, they definitely show deformation. And I've just been focusing here on the seismic data, but we do have the other observations. And there is definitely deformation with several of these stimulations, yes.
Okay, thanks.
And as we go to Greg, I can just suggest to you that you could share your screen without going into full presentation mode, and then people can see slides while you can also see them. Greg, go ahead.
Yeah, thanks, Ann. That was really amazing. It's a lot of work's going into this. So I guess I have a question about sort of the overall interpretation. It seems it's kind of related to the last question about whether you're getting, any detectable offsets in the boreholes or strains. It seems to me like if you have a maximum magnitude of a -2, but you're stimulating an area that's hundreds of meters, that presumably it's a lot of aseismic slip, or the seismic coupling is really low. Just wondering if that's consistent with your interpretation, and maybe that's part of the answer of why it's really different from the McGar line.
Yes, so I think, so actually my PhD student, she's working on the focal mechanisms, and I think we could speculate that the source size of the majority of these events that we have seen in this study is far below 10 centimeters, or even on the millimeter scale, actually. So I don't think that this accounts for the dimensions of fractures that we observe in the stimulation. And well, I think this allows to conclude that there must, so on the one hand, that the picoseismicity highlights processes on already pre-existing macrofractures in the volume, but also that there must be a large part of it are seismic. And I think this is, something that we need to investigate in more detail, also taking the geomechanical data that we have into account to really understand the full picture of what is going on. How can we have such large structures activated with, I think that goes in that direction.
Yeah, I guess just to follow up, it seems like these are probably tiny events that are kind of just mapping out a mostly aseismic process, but yeah, if you can inject really fast and generate something big, maybe that would help add information. Maybe it's just a low stress environment, and so predominantly aseismic slip is the way it wants to deform.
Yes, I think we are trying, like preconditioning so far certainly did not produce a larger event, so that we have already tried, but we are not giving up yet.
Thank you.
Thanks.
I have a question, but before I ask it, I'd just like to encourage everyone on the call to join in, raise your hand, especially early career people. This is a very easy audience to interact with, so don't be afraid to raise a question and to raise a discussion point for Anne. And quick question that connects to that one, and that is, I didn't catch if you changed injection rate throughout any of these. Was the injection rate always the same, or was there a variety?
No, so during these phase 2 stimulations, we did change injection rate. Maybe I can just give you a quick, you see my slides still on?
Yeah, we can see enough like this, I think, or you could just.
Let me go to, I pasted in some figure all of these injection protocols that I wasn't showing. No, not here. So, wait. So I mean, this is what we did. So interval phase 1 injection strategies were pretty similar for all of the stimulations. But if I go on, this is still phase 1. You can see we did pretty much the same thing. But here we come to phase 2. So we did try different things. Like here also in interval 11, we kept pressure at a rather higher rate for a day or so. We tried in interval 12 to do preconditioning. And so interval all these phase 2 were following different strategies.
I see. Yeah, well, I know that there's been some ideas that injection rate has a big influence in wastewater injection situations, and so I wonder if the event rate scales. Did you do any statistics of event rate as a function of injection rate?
No, it's a quite interesting point that I think we could do very easily. Yes. No, I will write it down and send you the results in a while.
Yeah, okay. And then one other quick thing before we go to John Rudnicki. There was a slide around 31 or 32 where it looked like the expansion was pretty asymmetric. Did you notice that too? You showed us the borehole, and it didn't look like the expansion was bilateral. It looked like the expansion
no.
mostly one direction.
Yes, it isn't. It is not. In most cases, actually, it is not symmetric around the borehole.
And does it always go up? And so this actually looks like it went down more than up.
So in most cases, it goes up, but there is, for instance, here interval 8, we suddenly start to have also something going down. Where is it? Interval 9, 10, it started around the injection point, and then it really jumps to a fracture zone that is at quite a distance. Also with a tendency of rather going up and down. And there was one where it really... No, but in general, I mean, most stimulations have a tendency of going up.
Yeah, I see.
Here we suddenly have something a bit further down in interval 8, phase 2, yeah.
Cool. Thank you very much. John Rudnicki, go ahead.
Well, Chris asked the same question that I wanted to ask about the injection rate. So let me just, so do you have plans to look at that more systematically or?
Well,
You
now
know-
that Chris mentioned it, yes, I will look at it.
Okay, well, I'll add my,
Yeah,
yeah,
we are
my
a very
interest in
small
that too.
team. We are a very small team at the moment working with these data, so we are a little slow in producing or in answering all your questions. So
Oh, well, you've got a fantastic data set there. I really enjoyed hearing you talk. So thanks.
thanks, John.
Ikram, go ahead. And others, please join in.
Thanks for the nice talk, and I'm just curious to know a little bit more about the coupling between the sensors. As you have mentioned, you have acoustic emission sensors in an array, and that has been hanging from a wire. And I'm just wondering how they have been coupled with the borehole wall, as well as the fiber optic cables as well, which you have used in this experiment. But I'm just curious, do you have any result output from the DAS cable as well?
Yes, we have results from that as well. So actually, I mean, we cemented the boreholes. So we did one experiment in de-stress where we had not cemented the borehole, and coupling is significantly worse than in the cemented borehole. So you definitely see that effect. I mean, these acoustic emission sensors, they are not clamped on the borehole. They are just attached to the rod for instrumentation. So you basically need to cement the borehole to have a good coupling with the surrounding rock volume. Otherwise, you will have the layer of water in between. So you do record some signals if you don't cement, but it's not comparable to the sensitivity in the final setup.
Okay, thank you. And one more quick one. Do you have find any relations between the newly created event and the reactivated event within the fractures, like in terms of moment magnitude or their clustering or any kind of observations you have noted?
Do you mean to differentiate between a fracture that already existed and one that was created?
Yeah, the newly created event which is happening, say for example, far away from the injection sites, and the events that are you have observed periodically that are associated with the shear zones and fracture zones.
So I'm not sure if I fully understand, but like at the moment, what we are looking at, for instance, is whether how can we explain the jump of seismicity from one area to the other that we sometimes observe. If this is like really actually the water migrating there, or if this is an effect of the stress and pressure. So we don't have the answer to that yet, but like my student, she's also looking, for instance, in this interval 12, where we had these new fractures. She's looking at the moment tensors there, and they do have a different mechanism in these small fractures here. Do I have a slide? Oh, well, it's very small here, but so she obtained hundreds of moment tensors for these small events, and she is looking at the dominant mechanisms from the different fracture areas. And there are differences. So we are looking at that in more detail at the moment. I don't know if that answers your question.
Yeah, thanks for helpful insight. Thank you. Very nice talk.
Thanks.
John Vidali, go ahead.
I think you just answered it quickly. I was going to ask you the systematics of the focal mechanisms. Are you seeing different areas have different stresses? Are you seeing any changes over time as the injection progresses? Just anything interesting about focal mechanisms?
Yeah, so I think there is a lot more that we have to do, because this is just one of the tiny intervals with actually where not that much was happening, and we haven't targeted the event or the intervals that have 5,000 events or so, which show a clear temporal evolution. So I think it would be very interesting to look there at the focal mechanisms and to also do an entire stress inversion of the area.
Oh,
Yes.
thank you.
Menendrine, I think you're still on the call. He gave a really interesting talk about focal mechanisms just a few weeks ago. Are these data amenable to that technique? Do you know, Anne?
Yeah, so actually I really liked his presentation, and I really liked these images, how he showed or he color coded with depths in the end. He did with machine learning a tremendously large catalog of focal mechanisms. And this is something that Martina has looked at last week. She just tried to color code in a similar way. But for interval 12, this is not so interesting because it's just a handful of events. But I think this is something that we definitely want to try when we are targeting the larger intervals to see if we have a dependence also on depth or on time or on different ways. Yeah, I mean, we are already happy that we can obtain actually hundreds of focal mechanisms from these tiny events, even though we just have the recordings of one component sensors. So, and I think they are quite reliable, what Martina obtains. Yeah.
Yeah, amazing. Other points? You know, and as you think more about this injection rate issue, I suppose the simplest thing is the volume that you put down there, because you measure that and you know it, and obviously that's going to be important. And I wonder to what extent, like, there's a trade-off between volume injected and the size of the thing you're injecting it into. If somehow like the flow rate on the fracture is important, that might be an interesting thing to think about, because your seismicity gives you some idea about at least 2 dimensions of the fracture that it's going into, and maybe you can back out the permeability estimate. So that would allow you to ask more detailed questions about the role of injection rate, because I suppose injection rate into a tiny fracture has got to be different than injection rate into a really big thing. So
Yes, but I mean, then again, if we go back to this mega, so we tried interval 9, 10, we stimulated separately small amount of seismicity, but then when we stimulated both of them jointly with a much, much larger volume, on mega we just remain on a parallel line. So we did not suddenly make a jump to something much higher. And we did try to push more there on the injection rate, not to maybe an extreme, because that wasn't the goal. I think that we will see in this M0 experiment. But yeah, injection volume was significantly larger. The existing fracture network in that area was significantly larger, and we did not really move away from a parallel line.
I see, yeah. Other points?
Also, if anybody has any ideas or more questions in the next weeks or so, feel free to send me an email. I'll be happy to try to answer or look into finding the answer for your question.
Greg McClaskey, go ahead.
Hey, and one other question. I think I read that the reactivation pressure was like 15 MPa. I was just wondering what your injection pressures were kind of in general, and how that relates to the overburden pressure or the maximum principal stress you think is.
Yeah, so the maximum principal stress about like 26 MPa. And here we have for the intervals, we at around, for most of them at around 15 in the first phase. And then it seemed to go a little higher or climb up a little higher for the reactivation each time. With the exception actually of 2 intervals where the reactivation was lower. Yeah.
Thanks.
But nothing very dramatic. And there seemed also to be a slight dependence on where you are, if you look here. So the reactivation also seems to be a little linked to where if you are closer to a shear zone or further away. But again, we don't have enough observations to fully conclude on that.
Ben Holzman, go ahead.
Hi, Ann. That was a great talk. Thank you.
Hi, Ben.
Overwhelming, really. So I may have missed this as usual, but the it looked like in yours, in the sort of time series plots, you had some experiments that were constant, where the pressure was fixed and the flow rate adjusted, and others where the flow rate is fixed and the pressure is adjusted. Did you address that sort of difference in the seismic response to those different conditions? Like it's not just flow rate as an amplitude that may be important, but also the boundary conditions.
So it's like our idea was normally to make it to do the same injection protocol in all of these intervals, so have pressure at a constant value and go up. But we have two of these intervals, they had such high transmissivity rates that we wouldn't go advance much. So we adapted and made it actually flow rate dependent. But the goal had been to stay in something comparable, so that we are in this characterization phase a little independent of the injection protocol and can really see how are these intervals, how is the rock volume there reacting.
So you can't really compare.
For those ones where we go with flow rate, I would say it's more difficult, but we wouldn't have been able to ramp up the same way with pressure.
Right. Thanks. Thanks again.
Welcome.
Any other points, not remaining questions? Well, okay, so we're perfectly on time, and you did a beautiful job of the talk and swift timing for us too. Thank you very much. So I'll ask people to unmute if they'd like to, but join me in thanking Ann once again. Fabulous talk. Really
Thanks, Ann. Thanks,
Thanks,
Chris.
great.
great to see you all.